welcome everyone. In this lecture, we will see an implementation of an attack, which in particular will be a padding oracle. And this will be our first CTF-like challenge. So to begin, we have to understand what are capture the flags and what does it mean to have a CTF-like challenge. So on capture the flags. So capture the flags, they are events related to computer science mainly, which can be either offline or online. So either people meet up or they just register to a website. And they are events like a competition whose main focus is learning by doing. So in this kind of challenges, there is no theory to study. There is only something to actually implement, something to actually do. And you test your knowledge, even your theoretical knowledge, by something practical. If you can write the code to do it, it means you know it. Otherwise, it means you miss some details. So in the context of computer security, which is the context of this course, computer network security, CTFs are a great tool because they are composed of a series of challenges. The objective is to obtain a flag, which is like a string, like a crypto is hard, something like that. But of course, to obtain that flag, you need to overcome various difficulties. And to overcome those difficulties, you need to first find the vulnerability, research how to exploit it, write the code that actually exploits it, and then you get the flag. Now, there are many categories of CTFs. Of course, what we will do in this course is focus on the crypto, because the crypto CTF challenges have to do with cryptography, crypto vulnerabilities. Vulnerabilities in the way that cryptography is implemented and used. Now, I think that CTFs can be really fun because, I mean, this learning by doing is something that I think university is a bit failing to teach. I mean, yeah, there are some projects, but it's like CTFs are more fun in my idea, but this is a university lecture, so I have to be careful. So our very first challenge, what is that about? So this is, I call this yet another oracle because in the context I had introduced other oracles. This is going to be our first oracle, our first padding oracle. So typically these challenges have use Python because Python is really easy to use. There are a lot of libraries. So instead of describing it theoretically, I'm going to show it in practice. So we have a server in Python, which we can run. Now here I've listed all this code is available on the teaching site. I've listed the requirements, which is just a single library, PyCryptodom, which is used to deal with cryptography. So to actually get started with the challenge, we can create a Python virtual environment with vuenv. Then we can do the source to activate the environment so that all the dependencies we install on these specific environments, we install the dependencies with pip /r to get all the requirements from the file. Now we have all the requirements. We can check out the challenge, which is made up of two files. One is the server.py and the other is secret.py. Now the idea is that in the context of the challenge, we only have the server.py code. We don't have the secret. The secret is stored on the server. So we can start the server.py. We're not going to check the code immediately. We just see the behavior, how it works. So we started a server. It says start of challenge, listening on 4444. So this is the port, the TCP port we have to connect. So in another shell, we go back. We activate the environment also in the other shell. So the first one, the top one is the server. The bottom one will be the client. So to connect to the challenge, first we can just use netcat. It is a tool to establish TCP connections. So we do netcat localhost because the server is run locally. In the case of a remote challenge, we would have to put the IP of the server, which will be given to us, and then the port, the 4444. So once we connect, the server replies to us with, "Hi, I've been told to show you this." Then there is an encrypted flag with CBCIS. I mean, this challenge is pretty self-explanatory. Typically, it is more first you need to understand this is made for educational purposes. So I already told you how this is obtained. So essentially, the remaining part of the string, which is this other part, is the encrypted flag with CBC IS. But of course, the problem is that we don't have the key. So we know that this is the flag, we know it is encrypted, we know how, with a block cipher IS in CBC mode. We just don't know the key. So it's not like we can take that and decrypt it, because we would need the key to do that. But it gives us a prompt so we can communicate with the challenge. If we like send random bytes, it tells us nope. It's like, no, something doesn't like about our thing. But if we essentially, if we reply with exactly what he has given to us, removing the spaces, so I think I have to remove the space. So it's only in one line. He replies with okay. If I like put what he has given to us, which is the encrypted flag, but I remove something like some characters, it's also gonna say no. So it's like we have this kind of binary behavior. It either replies with us okay or with no. Now, the thing is that with this thing at the end of this lecture, we will be able to decrypt the flag. And in general, we will show that in any given situation where we have this kind of binary behavior where we can understand if something is good or not, we will see what is good or not. This gives us the power to decrypt, which is not intuitive because one would not think about that. So in terms of actually the challenge, so we have a Python server, server.py. So we start it, it gets the prompt, then we connect and it shows the encrypted flag. And then we can like write a test, it replies with nope, we write the encrypted flag, it replies with okay. So this is good. Now, in terms of the code of the challenge, which we will not really cover the code, but we will cover the code for the solution. Now, this is like mainly Python code, as I said, and the only cryptographic things are like this crypto IS, get random bytes to generate some pseudo-random bytes, pad and unpad to perform the padding, which we'll see. And then, as we can see, the secret, the flag, is not found in the server.py, it's found in the secret.py. This is why typically in a challenge like this, you would only have access to like the server.py code. They will not give you the secret.py. So this is like some variables. Then like we got the end of the script because there is this main, if name equals to main. So this is like just to make sure that this code this execute only when we call it with the interpreter and not when we import it with other file. So if we import this file in other Python files, this would not get executed. But it is like Python syntax, it is not important. So the main body is the challenge tree main. And as you can see, here we have a series of global variables. The first thing we do is we generate the IV, we generate the key, and we create the IS cipher we specify the key, which was randomly generated using the size of IS. We will review a bit what is IS, how it works pretty fast. But essentially, it is a block cipher. It works on a 16 byte of data. So you give it 16 byte, it decrypts that and gives you in output 16 encrypted bytes. So the key has to be 16 bytes. And then there is the IV, which is the it is needed because we are using IS in CBC mode. So this is our cipher. Then we get the flag here, data to encrypt. What we do is, before the flag, we add some extra bytes. And this is done because in the attack, we will be able to recover all the plaintext bytes, but not the first block. The first block will not be available to us because of a series of reasons which we will explain. So I have to like put useless data before, just to make sure that we can decrypt the entire flag. Then what we do is we pad the data. So we do this function pad, data to encrypt with the block cipher OS. This essentially just adds padding bytes according to a specific scheme, which we will cover in the requirements for the attack. We encrypt it and then we encode it in base64. Then we print the prompt. We start this server. Fundamentally, this is like a TCP server. And we say that to every incoming connection, we execute the function incoming. Now, this is like Python details. We don't care about this. But essentially, this is just a stub. Like we use Python libraries to implement TCP server easily. What's interesting to us is this challenge function. Now, every time a client does a request, anytime I connect with NC and send bytes, here is the request will contain the data. So at first, I send the initial prompt, like, hi, I've been told you to show you this with the encrypted flag. Then I wait a little bit. And then at this point, I interact with the client queries in a while true. So it is until there are some errors, I keep doing this. So I get the client query, like if we remember when I connected to the thing. So here I connect, this challenge gets executed. First, I get sent the initial message. Now I can interact with the server. Why? Because the server starts to listen with the receive. I can send some data. As soon as I send some data, the client checks if there are actually data, if there is actually data. And if there is, it calls internally this Oracle function. Now, depending on the output of this Oracle function, if the output is true, I get OK, otherwise I get nope. So this is why we have this true behavior. Sometimes the function will return OK, sometimes the function will return nope, will return false, and so the server will return nope. At this point, okay, one can ask, okay, how does this Oracle differentiates between true scenarios and false scenarios? So the last thing about the challenge is this Oracle. Now the Oracle receives the payload from the client. Internally, it has the IV and the key that was used by the server. So first I decode the base64 payload. Then I create this new cipher just to be able to decrypt it properly, fundamentally, because then I do a decrypt. And to decrypt, I have to tell the cipher to use the same key and the same IP. Otherwise, the decryption will fail. Now, at this point, I will do unpad. So here I do unpad. I remove the padding. If at any point in this process, I get an error, because this is all in a try except block, if any of these functions fail, I return false. Otherwise, I return true. So I get true when I have a valid encrypted text, which we have to understand carefully that when we decrypt, if I get something that is not like properly sized, I could get an error. Another thing that I could get an error is if when I decrypt it, I get improper padding, because when I decrypt, after that it's gonna remove the padding. So we will see why this matters. So typically this will fail mainly if I have improper padding. In this case, I return false. Of course, if I send like 2 bytes, it's gonna fail because IS cannot decrypt 2 bytes, only 16. But we only will send the multiples of 16. So this is the overview of the challenge. Now, in terms of, this is what I said. Now, in terms of actually the attack, so of course the goal is to decrypt the flag, but without knowing the server private key. So this is the goal. We will see that this is possible. And what does this teach us in the end? It teaches us that this Oracle is an information leak, which is dangerous and should be avoided. And this time is like explicit. I return directly true or false. But in a real world scenario, it could be that it is not as explicit and easy to understand as this one. But maybe it could be that if I decrypt correctly, I respond very fast, like I don't know, some milliseconds. If I have some problem, I respond a bit slow. Now, if the attacker can measure this difference, it could be also like an information leak. And this information leak is in function of the key. So this true or false actually reveals something not really about the key directly, but about the key with the payload. It is like this kind of link. So we can start to understand how to actually solve this challenge. And this challenge is solved by implementing a PKCS7 padding oracle attack. And at this point, one can ask, okay, what is a padding oracle? And the padding oracle has to do with all this kind of stuff. So we will repass what are block cipher in CPC mode. We will check how this padding scheme work. We will understand why this MAC-THEN-ENCRYPT scheme is like could be problematic, and this links us to TLS, and then we'll talk about oracles in general. So AES-CBC. Okay, AES is a block cipher. Block ciphers work on specific size data. For example, AES is 128 bits, which is 16 bytes. So I give it the plain text bits. I put this in the block, and it gives me the ciphertext. I can see it as a black box, input, output, same size input, same size output. Now, the thing is that this tells me only how to encrypt a single block. But if I have, for example, a message of 32 bytes, I have to like link the various blocks. So a way to actually link the various blocks is through the CBC mode, cipher block chaining, which works as follows. So I have an IV, which is like another vector of 16 bytes. So these are 16 bytes. And then I have my plain text blocks. So the plain text I divide in blocks of 16. So there are all 16. 16 here, 16 here, and 16 here. Now CBC works as follows. Before actually encrypting the plain text with the AES block, I first XOR it with the IV. Then I put it in the block because the XOR does not change the size. So they are both 16. The output will be 16. And then I get the first ciphertext block. Then I use this one, and I concatenate this with XOR with the second plain text. Now, at this point, one could ask, why do we do this kind of weird construction? And it is because if you encrypt the same message 2 times without this IV, you would have the same output. But if you now introduce the IV allows you you can encrypt the same message 2 times, you just change the IV, and the message is completely different. So this is why this is kind of useful. And so like this is the encryption formula. So we have that the first ciphertext block is obtained through the AES encryption block, which takes in input the private key and the output of XORing the IV with the first plaintext block. And this is the same for all the others. In terms of decryption, instead, what do? We take the encrypted block, we pass it through the AES, but what comes out of the AES is not the actual plaintext block, because we have to remove the effect of the IV. So we have to XOR it again with the IV, and we get the actual plaintext block. The same thing, this is where this picture tells us why we cannot decrypt the first block, because essentially the attack, consider the second ciphertext block, which here I call the C1. So we have C0 and C1. So C1, to actually be decrypted, so we go through the AES block, we go through the XOR, but the XOR is done with the previous ciphertext block. So the attack we will implement is going to be like this. I manipulate this block. Okay, here I put some malicious stuff, so that when this XOR happens, I change fundamentally what is going to be the final plaintext of the second block. And this will literally let me see this M1. But to get M1, I need to manipulate C0. And so the same applies for M0. To get M0, I will need to know and manipulate IV. But this is typically not transmitted, so like it is implicitly used by server and client. So they are synced with the same. So this is why we cannot decrypt the first block. And in terms of decryption, we have this formula. We have that the first plaintext block is obtained by IV XOR the output of AES with the key and C1, the first ciphertext. And so, as you can see here also, IV we do not know, but we know C1, we know the ciphertext because we see them on the network. So we can manipulate this thing. So this is the idea. Of course, this introduces an IV. An IV should be like, there are some things to be aware when using IV. For example, if they are predictable, there is another attack, which we will not cover. It's called the BIS attack. So, I mean, the IV are useful, but they must be managed accordingly because you have to take care into the various things. So, of course, we said that AES works on blocks of 128 bits. But the question arises, like, what if I have a block which is longer or shorter or something like that? The basic idea is to introduce padding, and in particular, this one of the most famous padding scheme used is this one. It's called PKCS number 7. So it works as follows. It is introduced in the RFC 5652, and it says the value of each added byte at the end is the number of bytes that are added. So, for example, suppose that we have a block size of 8 bytes. It's like 16 bits. So in this first, I have only 2 bytes of plain text. This means that I need to add 6 bytes. Here there's a space. I forgot to add a space. So it means that I need to add 6 bytes, and the value of each byte is going to be 06, because it is the number of bytes that I add. These 6 bytes, 2 plus 6, is equal to 8, and I'm good. So in this other case, we have 4 bytes of plain text. To get to the next block size, which is we have to add 4. So we add 4 padding bytes of value 04. And this is the same for the last one. We have 6. We have to add the 2 bytes of value 02. So this is like the idea. For example, if we have 16 bytes, I have to add, here I have like 11 bytes to add. So there's going to be 0b because it's in hexadecimal. 0b is 11. So this is really crucial because we will exploit this fact. Now, about MAC-THEN-ENCRYPT, I think that Professor Bianchi already told you about TLS. And of course, TLS offers various cryptographic services, such as integrity and confidentiality. So AES, by default, only offers confidentiality. It only encrypts. It does not guarantee integrity of the data. If an attacker changes the encrypted stuff, I may not be able to recognize this. So we have to add other integrity. And in TLS, the construction uses first, I compute the message authentication code for the integrity, and then I encrypt everything. Now, this scheme, with a stream cipher, it works fine. But with block cipher, this choice of first integrity, then confidentiality, has a little like intermediate step, because after I compute the MAC, which is computed on the TLS data, then I start to encrypt. But at that point, the data may not be a multiple of the block size. And so before actually encrypting, I have to add the padding. But now there is an issue because I've added the padding after I've computed the message authentication code, which means that I could not have possibly included the padding within the MAC computation. And so what does this result to is that the padding is not integrity protected. And this is going to be the crucial aspect of our attack. An attacker can change the padding, but the server will not be able to recognize that the padding has been changed. So yes, so integrity protection does not cover the padding, because if the server maybe wanted to protect from such an attack, like we as an attacker, we will change the padding, but the server could say, if the padding has been changed, I do nothing. I do not process the message whatsoever. Now the server cannot do that, and so this is like this is a problem. Of course, if attacker can change the padding, will not be able to recognize. This is a security problem. These bytes, yes.
The example you did before the padding, are we not considering the length of the padding, which was the final bit?
What do you mean the length? Like here I have added.
The byte as how long is the padding?
No, the padding is like you can to actually like if you have a message, you decrypt it with AES, then you check like the last byte, and the last byte tells you how long is the padding. Yes.
Yeah, and in the examples, like the one we had like the 2 bytes, maybe the last one.
Yes.
Shouldn't those be like 0101? The final one says there is only 1 byte for the padding.
Now here I have 2 bytes padding.
So the length is not like comprehended in this.
No, the length is the value of the last byte. Yes, like look at this. I have 2. The length is 2. The value of the last byte is 2. Here the length is 6. 1, 2, 3, 4, 5, 6, and the value of the last byte is 6. So like length and value for this kind.
The professor says like the length is not comprehended, so it's different. Like
yeah, I think.
What is that?
I'm not sure. Like there are like maybe there are some version in which you like put 1 minus, like you put like 0.5. I don't know. Like I know like this,
Okay.
but like now depending on the specific, like do not like meddle too much which the specific working, because this can be implemented in multiple ways. But the idea is that the padding, depending on the specific scheme you use, by reading the padding, you also know the length. So I'm not sure. Maybe like you get the byte and you add some values extra. So the thing
on the slides of the professor, there was an extra box that says the length.
Yeah, like maybe it's different. I'm not sure. But in this scheme, like if you think about this scheme, it is like implicitly in the value. Maybe if you don't have like this kind of implicit value length equality, maybe you add it at the end.
Yeah, it was explicit at the
Yeah.
end, but it's
So it's like maybe you, yeah, like for example, if you do like 0.5, 0.5, you do like 5 of these, 1, 2, 3, 4. I don't know, like you can get like some padding if you here you add the length. If on the last byte you add the length like 3, then maybe here you can put whatever, and you know that those are padding. I think that in this scheme, like it is implicit in the last one. I will have to check the slide. Maybe I remember that they were a bit different. But see, yeah, so this is the idea. So we said that this is problematic because the attacker can actually perform this thing. But of course, this by itself is not vulnerable. The vulnerability comes when we have an oracle. So when we have this construction, we are safe yet. But then if we introduce an oracle, we broke confidentiality. And when we attack this thing in real world, understanding how the padding works specifically is really important. So we also have to understand the specific implementation details of the padding, because maybe with the Professor Bianchi padding scheme, the attack would be implemented in a different way. With this padding scheme, it is implemented in a different way. So about oracles. So what do we mean with oracle? So they were mentioned one of the first time by Alan Turing PhD in 38. So ideally, intuitively, an oracle is something that answers a question. So you have a question, you pose it to the oracle, and it gives you the answer. So for example, it could be like a number theoretic problem, like what are the factors of this number, or is this number a prime? Like question like that. Every time you have a question, you could have an oracle, which is an abstract representation of a mechanism to answer that question. So the thing about oracles is that we do not have to understand the details. We just have to understand the output. It is, we go back to the black box discussion. We just need to understand what the output is. So we have a question, we pose it to the oracle, and it gives us the answer. Of course, the answer might be implicitly in the behavior, like query time, response time, or explicitly as in a challenge, yes, no. Like if I have no, okay, this is an answer. The question was the byte that I sent. Of course, different oracle might answer for different questions. This is an example, but we don't care about that. Of course, in our specific code, the challenge offers an oracle on this specific padding scheme. Because if the message we send, once it is decrypted, it respects the rule of the padding we introduce, then we get an okay. Otherwise, we get a nope, meaning we get like, this is not good. And so mathematically, the oracle is like a function which gives us 0 and 1, depending on our ciphertext. So this is the payload that the server receives, the entire message, the entire blocks, the sequence of blocks, and it gets 1 or 0, like okay or nope, depending on whether the plaintext. So from the ciphertext, the server uses the key to get to the plaintext. So the server needs to know the key. And then once we have the padding, we ask, is it okay with the padding scheme PKCS? Is it padded correctly? If it is, we get a 1. Otherwise, we get a 0. And this is the code that implemented the Oracle in the challenge. So in terms of the actual attack, and we can actually, like, to get some intuition, what we can do is we can stop the challenge and change, like, to understand how this padding works. What I can do is, again, like, print this stuff, and I can do is I can pad the data to encrypt. First, maybe I print it. First, I print it, then I print it with the padded data. Then I print this padded data. This is just to show. So as you can see, so data to encrypt. So here, look at this. So here the A at the start are like the garbage bytes that I added, okay? Then there is the flag, which I mean, I shouldn't have shown it, but whatever, this is at the end. And then I add the padding bytes. So you see 03, 03, 03, because there are 3 bytes. Of course, this depends on the specific implementation, but this is the idea. So in this code, we work with this. So this is the padded data. And of course, when we encrypt it, after we pad it, we can encrypt it with the cipher, encrypted data. The data, and if we then pad the data, this is wrong. First we pad it and then we encrypt it, and now we get this, like, these bytes. So this is like weird bytes because this is encrypted, so they are not, of course, recognizable. And then by base64 encoding it, base64 encode, we get back what we saw in the challenge, which is this value, which is more recognizable, but still it is the base64 of the bytes. So in terms of the solution, so with respect to, I don't know what the fuck happened here. So consider this notation. We have a bunch of plaintext bytes and a bunch of ciphertext bytes. We suppose that we have like m total blocks, but this is not important. And this other notation, which will be useful. So we identify with PIJ, we consider the jth byte of the ith block of plaintext, because the plaintext is divided in blocks. So this can be a bit confusing, but we will just use it a little bit. So like this is, for example, P1, this is P2, and this is P3, but P3, not B, P3. But each plaintext is 16 bytes. So we have like P11, P12, until P116. And this notation will be useful because we will have to mention like specific bytes of specific blocks. So this is kind of useful. And we denote with n the length of the block cipher in use. So for example, this represents the encryption of the first plaintext block. We go from P1 to C1. We go from each byte of the plaintext to each byte of the ciphertext. So remember, C11 is the first byte of the first ciphertext block. C1n is the nth byte, which we can assume that n is 16. So this is IS of the first ciphertext block. It's like if we have the view of before about like the IS construction, but this kind of the way I showed it here hides the fact that so we can mention specific values within these blocks, and they will be useful because to get this like plaintext, we will have to modify the last byte of this ciphertext. So we will have to do this kind of things. So what do we do? Now let C1, C2, C3 be the various ciphertext block. Let the IP be the initialization vector. So remember, this is gonna be useful, but we will mention them when we need to mention them. So now we focus only on decrypting the C2 block. So only P2, because as I said, P1, we need the IV. We don't have the IV. P2 we can because we need the C2 and C1. So we only consider the first two blocks and the IB. Of course, the IB is implicitly because we don't really use it. But so C1 and C2. So the idea is to find the second plaintext block 1 byte at a time. And this kind of attack is very like, it is a general recipe. It is also found, for example, in the blind SQL injection in the web context. So to this idea at first is a bit confusing, but when you get like the idea, you can use it in other contexts. So instead of brute forcing the entire block, we will start from the last byte of the block. So this is P2. We have a bunch of bytes here. We'll start from the last one. Now, if we consider only the last, how many possibilities do we have? This 1 byte, 564 possibilities, because it is 8-bit. So we will ask at most 256 questions to get the last byte of the plaintext. So the attack is not like, I'm not be able to like directly go to the one, of course, but I can reduce the surface attack by a lot. Because if we had to brute force the entire block, okay, that would be like 16 bytes. So 16 bytes is like 128 bit. So this is 2 to the 128. So to get one plaintext blocks, I would need to do 2 to the 128 questions. There are a lot. In this case, we need to do 2 to the 8 for the last. Once I have the last, I can go to the second last, the penultimo. I don't know how to say in English. The penultimo. And to get the penultimo, we need another 2 to the 8, but we add them. Then another 2 to the 8 for them. So at the end, we will have a sum of how many 2 to the 8. They are like n, because it is the block size. So like 16. So 16 2 to the 8. This is like very, very, very like small. So we will ask, is the last byte equal to 0, 0? Is the last byte equal to 0, 1? Is the last byte equal to FF? So a random question. I give you like a general, you can swap for one with anything you want. We can start by asking, is the last byte of P2 equal to 0x for 1, which is A, using ASCII encoding. So, and using our notation, we can replace the question with this, is P2n equal to 0x for 1? So this is the question we want to answer. Now, the idea is, I listen to the network, I get the ciphertext blocks, and then I change the C1 block. I create a malicious payload. How? I don't change all the bytes. I change only the last one in a very chirurgical way. I don't know, like a very specific way. The remainder, they are untouched. The last one is going to be not only the value of before, but I XOR it with other things. I XOR it with 0x for 1 and 0x01. So this 0x for 1 comes from our question, because we want to test the last byte. This 0x01 comes from the padding rules and the fact that we are trying to break the last byte. So in the attack, these kind of values will change. When we, for example, change this other byte, we will have to change those values accordingly. Now that we have constructed this new ciphertext, we send it. So there's the old and there's the new. Now the new is like the previous message, doesn't change anything. Of course, we don't send the entire message. We only send the prefix. This has to do with the AES construction, because now the entire message is not valid in the sense that having changed something about this thing, this will change. So like everything changed. So if then he tries to decrypt the further blocks, you will get an error. But the first blocks are okay, because the first block we did not change anything. So we only send the prefix. So for example, if instead of wanting to break P2, we wanted to break P3, we would change C2 and we would send like C1, C2, C1, C2, C3. We would change this 3. We would send this 3. So we will not send C4, etc. Now we send it to the server. The server has an oracle, we assume. And for example, suppose that the oracle replies with 1, replies with, okay, good, this message is good. We have changed the message. I mean, on the original challenge, by default, the server always replies with, okay, if I give it the default ciphertext, the base encrypted flag, because the base encrypted flag, it is by construction correctly padded. So if I just connect to the server here, I give it back exactly what he has given to me. It's going to be okay by construction because he decrypts it. It is correctly padded since the server is the one who padded it. And so this is okay. This not gives me much information. But now I have changed the ciphertext. So this okay reply gives me something to work on. What exactly? What is it that we can infer? Now, if we remember how the construction works, the last byte of the new plaintext, so how to obtain the new plaintext, we add to XOR the last byte of the previous ciphertext, which we have changed, with the last byte obtained by the AES decryption. So here I should have a photo. So it's like what we're talking about is like this thing. So the last byte of the plaintext, M1, is obtained from this AES, the last byte of this AES block, and the last byte of this. Now, we have modified exactly this, so that in the XOR, this kind of leaks. And the formula is this one. So how to read this? We have the last byte of this new plaintext, which is obtained from the last byte of the ciphertext that we changed, of the malicious ciphertext, plus the decryption of AES, plus the last byte of the decryption of the AES block. So I think this confuses because we are talking about single bytes, but the N is the single byte. We needed to work on the single byte because this is where we leak information, one byte at a time. Now, if we replace the ciphertext with our payload, because this new ciphertext was constructed in this specific way, by taking the original one and then XORing it together with 41 and 01, and then there is the old, like the default AES decryption block. This means that we can rewrite this as this thing plus this other thing. Now, this thing, the thing on the left, with this parenthesis, is exactly the same that happened before we change anything. Because before we change anything, to get the last valid plaintext block, we sort together the last byte of the first ciphertext block with the AES decryption procedure on the second ciphertext block. But now there is this extra stuff. There is the 041 and there is the 001. So essentially with this, we have forced the last byte of the plaintext, of this new plaintext, to be this formula, to be the last byte of the original XOR together with other things. So yeah, this is the idea. Now, we know though that this is correctly padded. So we know that what can we infer from the fact that it is correctly padded? For example, suppose that, so this is P, I will write like P2 like this. So this is the final second plaintext block. If it is correctly padded, it means that, for example, it could start with 01 and then other bytes. This is a correctly padded value. Or it could start with 02, 02, and then other bytes. This is also correctly. Or it could start with 03, 03, 03, etc. Now, we know that this is correctly padded, so we know that this value is either equal to 01, and that's it, or it is equal to 02. But if this last byte is equal to 02, the previous one also has to be equal to 02 because they have to be consecutive. So we can do a series of logical consequences. For the plaintext to be correctly padded, it follows that, for example, if, like here I have a bunch of cases depending on the value of the last plaintext block. We know it is correctly padded. So for example, it cannot be greater than 16 because the block size is 16. If it is correctly padded, it has to be less than from like 1 to 15, 16, I think. 15 though, because 16 would be full padding. So if it is 1, what do we know? Well, what we can infer is like we set this equation. We said, okay, this thing is equal to 0x01, but we also know that this thing is equal to the original plaintext XORed with 0x41 XORed with 0x01. So we put them equals, so equals this to 0x01. For this to be true, this has to eliminate with this. They have to cancel. To cancel, they have to be equal, because XOR cancels equal things. And so we have something about the plaintext. So this is a case. Now the attack is a bit involved because this is not the only case. Now it could happen that the last value is 0.2 and the previous one is also 0.2. This is also a possible case, but what is here the unrealistic scenario is that in this second case, we get something about the plaintext. This time it has to be 0x42, because if we do 0x42 XOR 0x41 XOR 0x01, we get 0x02. But this time we also have to make an assumption about also the previous value of the plaintext, and we have to assume that it is equal to 0x02. And this is highly unlikely. I mean, it could happen, but it is like really highly unlikely because it is also this is plain text. So it has to be like semantically meaningful to have this kind of 0.2 at the end. I mean, it could happen, but it is highly unlikely. And of course, the higher we go here, for example, for 0x03, we have the final plaintext value, but also we have an assumption on the last 3. The more assumption we make, the probability just drops to 0 essentially. So in practice, this never happens. The first one always happens, but theoretically it could not really happen like this. So therefore, if it replies with okay, we get okay, the last byte is 0x41, highly likely. Otherwise, we get like if it replies with 0, it means that it is not correctly padded, and so it means that it is surely different from 0x41. It is definitely another thing. So, for example, so if we discover the value, we go to the next byte. In the case of 1, we assume that it is 0x41, and we go to the next. If we have not discovered, if the oracle replies to us with like, no, this is not correct, we have to go to the next guess. So not 0x41, but 0x42. And the payload we construct is going to be here. When we construct the payload, we have to encode the guess in the payload. It's not going to be 0x41, it's going to be 0x42. The padding remains unchanged because I'm breaking the last byte. So the guess, like this thing is the guess, this thing is the padding. The padding has to do with which is the byte I'm breaking, the second last, and the actual value, it is the guess I'm making. So this is, for example, if the guess for 1 does not work, we go to the other guess, which is for 2. Now, if instead the guess works, we go to the next byte, which is actually the previous one in the order. It is inversed. So the question becomes, what is P2 n minus 1? Because now we have discovered the last byte. So this is P2. Now we know that this is for 1, but we don't know the rest. Now, the cool thing is that now, since we have discovered this thing, we can break this other thing, and we control the suffix. So we always control the suffix of the blocks we're trying to break. So how do we answer this question? So we start for 0x41, it could be 00, 01, 02, any guess. Analogous, we construct a new ciphertext. The most important thing is to understand how to construct a payload. Now, this time, we have to change the last 2 bytes, because so we go from C1 to C1 Cappuccio at. So the last byte, what is that? Is that the padding changes to 0x02 because we're trying to break the second byte. Here, I put the valid value, the P2N. And I put this so that in the original plaintext, this is going to cancel out. So here we'll be only left with 0x02. And since I've discovered this previously, I can do this. The second byte that I change is the second last, the penultimate byte. And I do, here I put the guess, here the padding, and here the previous value. So this is the main construction. Once again, this we discovered previously, we construct a new ciphertext, we send it. What we can, so suppose that the oracle replies to us with OK. What we can infer, it is correctly padded. OK, cool. Now, in this case, this is only possible in one case. There are no other cases. There are no other possibilities now. And there are no other possibilities because at this point, we control the last byte. So we force the padding to be whatever we want. So in the previous case, it could be that like the bytes on the last would form a correctly padded like by random, by possibility. This time it cannot happen because I don't care much about the next bytes. I put 2 padding, I control 2 bytes, and this is what I can do. Once again, in terms of formulas, so here I just put to make it more clear, I have this plaintext is obtained by XORing the output of the traditional n-1 byte, like this traditional construction, XOR with the modified payload. The modified payload is like this. At the end, I get back this thing. I get back this thing. This is for the n-1. And so, once again, if this is correctly padded, it means that this is equal to 0x02. It means that this eliminates with this. They eliminate, and so they have to be equal. So this is, I mean, this is essentially the idea of the attack, to do this kind of inferences. And so in this case, the oracle replies with 1, we know the byte, the value. The oracle replies with 0, it's not that 1, we have to increment. If we did not find it, we can increment. If we find it, we go to the next byte. So this kind of thing it works the same. So now I'm gonna do like 5 minutes, like 3, 4, 5 minutes, not too much of break, and then we will implement this idea from 0. So yes, these beautiful ideas in actual code, and we will start like from 0. So suppose that we have, someone gives us this server, and then we will write a new file, new solution.py, and we will write the code. Yes. So, guys, attention. Okay, so we write the code that implements what we discussed previously. So the first thing that I like to do is add this little thing, which is called a shebang. And it just says which interpreter to use to call the file. This is a small thing. Like for because if once we write the file, we can make it executable with a new solution. Now, if you do like, so chmod x new solution, so this is an executable. If you do like this syntax, it's going to execute it, but to execute it, it needs an interpreter. And so in the first line, he understands what is the correct interpreter. So this is like the first line. Then we'll have a bunch of global variables, like challenge EP, which is 1001. I could also have written localhost. Same, it's the same because it's the local. Challenge port, which is 4444. Then I have a variable which will hold the TCP socket. I'm gonna say none for now. I'm gonna have another variable which will have the encrypted message, and then another variable which will define the block size. I mean, this is, you can change it, it's just to start. So here I put this thing. And this is why I put this thing is that if now we execute Python, it's gonna execute this internal code. But if in another script we do import like a new solution, this code is not gonna be executed. So it is to say execute this code only if run interactively. See, this is the idea. And in this, so the main function of that we're going to implement is going to be called challenge solution. This Python function. So we'll have like a bunch of global variables. We put like challenge import, challenge EP. I mean, when programming, they tell you to not use global variables, but this is like to exploit, so I can do whatever I want. So global. So the first thing is we create the socket connection to the server. We do with socket. So socket.socket. So this is like Python to create the TCP socket stream, sock stream. And of course, anytime I use a library, I'm gonna import. I want to do this like on the go without like importing like 10 libraries differently so that we don't know what they are used for. So this is for the socket, of course. Then we set a timeout just to make sure that if there are no messages in like this kind of thing, in this kind of delay, the connection does not drop. Not really needed. And then we connect. We connect with, we specify a tuple with the IP and the port. Okay. And then we start to get the data. So server data uguale sock.resv, and we put 4096 bytes because this is enough. So we can execute it. So I'm gonna call the main code here. I'm not sure, probably I should put here so that it is better. Of course, I did not print anything, so nothing was seen. So this is the data we receive from the server. Now, of course, we have to like format and only extract what we need. So when you actually in real world, you have to do this kind of things which have nothing to do like with cryptography per se, but they are it's like you know, the exploitation. So what we're gonna do is we're gonna delimit the string so that we're gonna use Python string classes. So the first thing is like we get this thing, I think. So let's see. So we're gonna put encrypted flag. We're gonna take the text, exactly the bytes that the server gives us. I'm gonna put them as like the start delimiter, and the end delimiter is gonna just be the prompt. And the prompt is like so start delimiter and the delimiter. It's gonna be /n/n, this angular parenthesis and space. And this is all so that we can do like server data.find, then we're gonna find the index of the data. I mean, this can be done like in multiple ways, but this is just to extract only the encrypted flag. So we find the indices of the where it is, and find and delimiter. So this is essentially what gives us like 2 indices, okay, numbers. But we know that between those 2 numbers is the encrypted flag, so we can say encrypted flag is the server data, but we want to slice depending on the index computed. So we can print it. And now we get the encrypted flag. So like as I said, this is just mandatory. Now, the first thing is that the flag was base64 encoded, so we have to decode. So we do encrypted message bytes. We do B64 decode with the encrypted flag. And of course, if we run this, it's gonna say, look, you don't have this library, so we import this library. We do import this library. And I suggest to like develop an exploit like this. Like always start with the basic things, and then you can do the more fancy stuff.
How would we understand that it's the basis 64?
You Google.
Okay.
You Google and you pray God that someone brought it. Okay. B64. And then after, it's not this, it's actually import B64. No, it's import B64. I'm gonna cheat and use my notes. base64. Okay, so base64 is the module, import. And here I suggest to always take notes, like when you do it one time, so you search, then you discover, write it somewhere so that you can always look at your own code, because otherwise you will be crazy. Most of these things, they are repeated, like encoding, connection to TCP. They are like primitives that one needs to like work well. And to do this CTF practice, after some time, you get the idea. So I think that this is wrong because, okay, this is better. Resolution, invalid syntax. I forgot how to code base64. No, from. Okay. Okay, so this is this not change anything because I still printed the previous, which was the base64 encoded. So now I should expect to find a bunch of garbage. And another thing, when you write an exploit, you should always have like interactivity in mind. Like you make an assumption about the code, you check it if it's true, because like the code, they can be very complicated. So you always have to understand what is happening. Did I decode it correctly? Maybe I've read the exploit fine, but I don't decode correctly. So this is always important. So we do this, and then we can like get, okay, how many blocks do we have? Because now that we have the encrypted message, we can count how many blocks. And to count how many blocks, what do? We take the length total and we divide by the block size. So we get like a number of blocks. We do the length of this thing, okay, and then we divide by the block size. And here I did the // because this is an integer division. If I print that I don't have like floating or things like that. Yes, I mean, this is really not needed. It is just like I do this, I get 48. So the number of blocks, blocks 3.0. So it's like 3. So we have 3 blocks. So we have like C0, C1, and C2. Of course, which means that we have plaintext 0, plaintext 1, and plaintext 2. Of course, plaintext 0 is out of our reach. We can only get P1 and P2. So now we will define the list which will contain the plaintext. And now we will define this function, the decrypt block. We will put all the bytes of the message every time we put all. Then here we put the index of the block we want to break. We start with, I think, 2. And then we put the block size. So this function I have to define. So this is just like print second block decrypted, second plaintext. And then here I print the second plaintext. We have to define this decrypt block. So we will do here. So we define it, we get so this is the main function. We get the first argument, which is the encrypted text, the encrypted message. Then we have the, like, here I put n, which is the block we want to break. And then we have the block size. We could also put like other number. So encrypted text is the text we want to decrypt using the CBC oracle. N is the index of the block we want to decrypt. And block size is, it's block size. Yes. So we can do like an assertion, assert n equals to 1, because assert is like, if this condition fails, the program crashes. So we can write, sorry, cannot decrypt the first block, as we don't know the IP. Okay, now here we check if we are on the last block. No.
Ok, maggiore di 1.
Yes.
Okay.
Yes.
Se non è maggiore di 1.
Exactly. So here we check, we do a condition where we check if we are trying to break the last block, because in the last block something is a bit different. So we do if the len, like we can do, I think that we can do if the len divided by the block size, here I put the integer to have an integer, is equal to n, which is our index, then last block is equal to true. Actually, we can just do last block is equal to this condition. This means that, so this reduces to when we want to decrypt the last block, n is going to be exactly the length divided by the block size. So in this case, it's like 3, the third block. And so last block is going to be true. We take note of this because in the attack, we will like treat it a bit different. So what do we do? Now, we do guess so far is 0 times block size. So the guess so far represents the plain text of the current block we have found so far. It could be like plain text found so far. So it is this syntax is just to create a list of block size zeros, so 16 zeros. Of course, we will populate as the attack progresses with the actual values, starting from the last to the first of the 16 bytes. And then we saved bytes. So saved bytes is going to be encrypted text of block size times n-2, block size times n-1. And this, now this thing, we want it in bytes. So we have to do this kind of thing. Now, what does this do? For example, print saved bytes. Here I'm taking a specific chunk, encrypted block. For example, if I call it, so I have 3 blocks, right? So here I can call it with 2 and 3. It makes sense to call it 2 and 3. If I call it with 2, what happens is that I get second block decrypted. Okay, this is so 48. I don't give about that. The plain text, of course, here I'm not gonna print. So we have this, and if we print the entire message first, so entire message, what do we get? We get encrypted message bytes. So the entire message is like this XAB, E8, etc. And this thing is essentially the first, I think, XBC. Okay, it's the first ciphertext block. Because as we said, what we do is to break. So if we have C1, C2, and C3, which we have, in these saved bytes, okay, like, okay, you want to break this thing, I have to save the previous one. So we save the bytes of the previous one. We save them so that when we change them, we can recover the original values. Because then we will modify these ones, we will create a new ciphertext, and we will decrypt the things. So this is like the bytes of the previous ciphertext block. This, of course, is in function of n, depending on the value of n. So I can probably save block of previous encrypted block depending on the value of n. Okay, at this point, okay, so now we have to decrypt the entire plaintext block. So we have a first for loop, which we go through the block size because we have to decrypt 16 bytes. Now within this, what we do is we set the padding value, which is going to be I+1. And this is accordingly of what I said, the padding has to be added every time we decrypt a new block. For the first one, it's going to be 0, 1. And here, the range is from 0 to block size. I mean, here is like programming things. I could start it from here to this, and it would be like I. So it's really the same. Maybe this, I don't know, like I'm going to do like this. Just to say though that the range has to be 1. Yes, yes. Okay. So the padding, first the padding is 0, 1, then it's 0, 2, then it's 0, 15 at the end. It's like 15, which is FF. And so this is how to deal with that. Then we do like a found variable, which is false. This is gonna say, in this current iteration, did I find the correct byte for this position? At first we did not. And then I save the message. Now the message, I'm gonna save it as encrypted text D. From the start to block size times n. So what do I do here is I take the entire, suppose that I have like C1, C2, C3, C4, C5, but I'm interested in breaking C2. I don't need to save all the others. I can only get this prefix. I can only get this thing. I can only get this prefix. And for this thing, I take all the bytes up until the nth block. So this is the idea. Now, what do I do? Well, at this point, there is the internal for, which goes through every possibility for the current position for C in range 0 to 156. All possible values for the byte. Now, here I'm gonna do handle case of last block. We're not gonna do that right now. We're gonna check that later. So what we do is, now the guess so far has to change, because now we have to, here we are doing at the start of this, okay, we're saying, suppose that the ith byte of the plain text is the value C. So we have to update our knowledge. And to update our knowledge, what do we do? Block size -1 minus I, -1 minus I, equal to C. This is because, as we said, we do in reverse order. So we start from the last to the first. Here, I ranges from 0 to block size. So to get like, if I is 0, I need block size -1. If I is 1, I need block size -2. Because the plain text that we discover is gonna first the last, and then the last one is the first one. The last byte we discover is the first byte of the plain text. So there's this reversal, and this is replied with the indexes. Now we prepare the payload. This is the part where we encode the this kind of formula, this formula. We're going to encode this. So how do we do that? Well, now the payload. To prepare the payload, we have to consider that depending on which position we want to break, we will have to change a different number of bytes. For the last position, which is the first byte we break, we only have to change 1 byte. For the second, 2, for the third, 3, and so on. We do a for, I don't think that is good, J, for J in range 0, I plus 1. So this is like I iterations. Actually, I plus 1 iteration, because I starts from 0. Now, here I do this global index and relative index. I do this computation before actually changing the payload. Now, the relative index is block size minus J minus 1. And it represents the position within the current block I want to break. Where, for example, if J is 0, this represents the last position, which is like the 15th position. Then if J 15, 14, and so on. And then there is a global index, which is the index with respect to the start of the message. So we do block size times n minus 1 minus J minus I. So this is like, I mean, the difference is that here it's just that, for example, if I have C1 and C2, the global index starts here at 1, the relative starts here at 1. And they are used to actually prepare the message, because the message is going to be global index, because I want to change the actual message, so the final message. So to actually change the correct byte, I have to offset from the initial. And then I do saved bytes, relative index, I XOR it with guess so far relative index, and then XOR it again with padding. Now, this thing is the Python encoding of that rule, where saved bytes is the original. It's like C1N. XORed with the guess, like 0x41. XOR with the padding, 0x01. Of course, all this index and all this like complexity is the fact that I have to automate it over all the bytes, over all the blocks. But this is like why I have XOR. I have two XOR of 3 things. And here I'm changing the message. I mean, what could implement it differently where you change the specific blocks and then you combine the blocks and you send them together? This is another thing. So now we have prepared the payload. We have to test payload. To test payload, we do query oracle with the payload, with the bytes of the message. Now, query oracle is, we have to implement it. It is our interaction with the server. So suppose that we can send this payload to the server. Now we will assume we will implement later. To do implement this later, this payload. So we continue depending if r equal to true, or we could say simply if r. So if the oracle says okay, we can essentially do okay, we found it. If the character, the byte is printable in string printable, and here we have to include this thing, import string. If it is printable, we print it. Like if it is A, we're gonna print it. If it is like a /n, we're not gonna print it. So we do print with the format string. We do, so this is the thing we do. Here we put the index of the block. Then we do byte. We get the offset of the byte within the block is, and then we get the value of the block. The numerical value and the character value. So this is just completely printing. Otherwise, we print it, but we just like we do not print the non-printable. So we put non-printable byte. Printable byte. The rest is like the same. Okay, and then after we found it, we break. We don't need to try the future possibilities. We just okay. Now this thing, we need to implement 2 things and then we're done. So it is not really that hard, but it requires a bit of delicacy. So we need to implement the test oracle. So here I'm gonna zoom. It's called query oracle. Query oracle. So the query oracle. The query oracle is this one. Okay. So the interaction is pretty straightforward because we get the payload. Then we, of course, use the global socket. And then we do, first we encode, x64 encode of the payload. We have to prepare it so that the server can understand it. x64 encode. Then we just send it, pretty socket send, encoded payload. And then we get our reply from the sock receive, 60 like this. Now, if okay in byte, this is like B is like saying in bytes, in Oracle reply, we return true. Otherwise, we return false. And this statement can be reduced to simply return okay in Oracle reply. So like this. So at the end, the query oracle is pretty forward. I have the payload, I basically for it, I send to the server, I get the reply. If it contains okay, I give a true. Otherwise, I give a false. Now here, it seems like we are done. But let's try it like this. So 16. And there's bytes object does not support item assignment. Okay. Did I do bytes? Bytes save bytes. Okay, foreign range. I think, sì, list. Ah no, here I forgot list. And this is why I put a list to remove that error. Okay, now, because like here you have to also battle with the programming language, and like the lesson here is also to like this kind of error. It's like you will encounter many such errors, and you have to accommodate the code to, you know, it's like this is because he considers bytes to be mutable, and here I was changing the bytes. So first I get the bytes and I put them in a list. A list I can change the list, and then when I send them to the Oracle, I transform them back into bytes. So I have to do this kind of conversions. Now, when we executed, what did it do? It said second block decrypted. So we get byte 16 is T, byte 15 is P, and so on. So for the second block, we decrypted the second block. Now, we have to decrypt the third block. So what do we have to do? We have to do print second block, print third block. Third block decrypted. Here you have to put a 3. Okay. This is going to be third plain text. Third plain text. So let's see. I'm going to comment the second. So here it's going to like do something weird. So it's not really going to work. And this has to do with the last block that I was talking about, because this took me a while to debug when I saw it, because like I was like, okay, it works on all the blocks, but not the last one. And the last block, because this is not only the last block we're interested in, this is the actual last block of the valid message. And so there is a condition which I did not consider, and C3 by default has proper padding. So C3 starts by default with proper padding. Now, in this case, we always get this kind of thing, because when like in the code, we always get 1 as an answer, which is not really true, and also the rest fucks up, so it doesn't work. So we always get 1, because what we do essentially is, if we look at the code, so suppose that we are on the last block. So on the last block, cool, what do I have? I have here, I start with padding 1. Then I start with C0, so padding 1, C0. My guess is going to be 0, so I assume that the last byte will be 0. And I generate this new payload. But this new payload, if we check, like, suppose that C3 is like the last. So the new C3N, what is going to be? It's going to be the previous one, okay? It's not going to be the previous one, it's the plain text I'm actually referring to. So the plain text is going to be the previous plain text. So fuck me. The previous plain text like this, the original one, but now it's XOR with my guess, which is 0x00, and with like I think the value of the padding, which is like 0x01. Now the thing is that maybe it doesn't work for 00, but at some point C is gonna be like here. I think that if okay, I'm not sure if I remember correctly, but essentially there was a case, I think that I wrote here in a comment. The last block is only because of when guessing the last byte with the value. Okay, so our guess, suppose that our guess is not 00 but 01. Okay, so we are decrypting the last block. C is 1. The padding is 0x01. And the last block is valid. This is like valid padding. So when we modify it, so this is the modified version. The last byte of the modified version will be the original, XORed with or guess, XOR with the padding. Now to here, the padding and the guess, they are both 0x01, so they cancel, and I get the original plaintext. In the other blocks, this will fail because the original plaintext is not really well padded. But in the last block, this will always give me an OK because it is properly padded. So what does this mean is that in the last block of the entire things I want to break, even if the oracle replies me with OK, like the case where the guess is 1, I have to not to really try for a positive. I have to test all the other possibilities. And if the all others are negative, then it is a 0-1. Because if I try with a 0-1 like this, it's gonna like fuck up and say this is true, but it's not. Simply because it's gonna eliminate with the padding, and I'm lucky enough that the last is already correct. So like in this code, like for example, I don't consider the possibility where the one I mentioned in the slides theoretically, where you have to go back. That would complicate the attack, but in practice, like this rarely happens. But if something doesn't not work with this code, it's probably because of that. So to actually fix this case, what do we have to do? We have to say if we are on the last block, and so if we are on the last block, and the I is equal to 0, which means that this is another way of saying, and the padding is equal to 1, and the guess is equal to 1, then I have to do a continue. So this is one of the rare cases where continue actually is used. Because I have to skip this case. This case I cannot really check directly. So I skip this case, I do all the rest. And at the end of this for, at some point, either I've already found it, and so I have the break here, and then I go home to the next byte happily because I have discovered it, or I have not discovered anything, and so it is the case that the last byte was actually 0-1. So here, after the for, I do if not found, if I have not found it yet, if not found, and I'm on the last block, and I and padding is equal to 1. In this case, I can do guess so far, the block size minus 1 minus I equal to 1. And then that's it. And then at the end, I return guess so far. Did I even return it before? Not sure. And then at the end, I return guess so far. Because I printed them, okay, I printed them one after the other. So in this case, now, we execute it. I get 333, which is the correct padding. So I am able to discover the correct padding and all the rest of the message. So before this, it didn't work. Now it works. Final note, and then we're done. We can implement this in a for loop to suppose that we had more than 2. I see my function for all the blocks. So I do plain text plus equals the crypt block procedure. Now the block is going to be I. It's going to be like the ith block starting from the second to the last one, which is the number of blocks I have. And here, of course, I will get the plain text reversed. So if I print this, because we like the order is reversed in a way. What the fuck? Yes. So here, this is probably why I put the integer division, because then I use it in the for. So there's always a reason, and the reason is to not go crazy. So here we have a bunch of bytes, and then to transform those bytes in like text, so that we can read it, we can do like, so we can do plain text, we can do a join of, first we transform each, okay, so this is a little bit, okay, so what we do is, first we do a map, which takes a function and a list, and this function takes the element of the list and gives us its character representation. So this map returns us a list of characters. No, it is a map object. I have to transform into a list probably. So I have to transform into a list, and then I have to print it. Yes. So this thing. And then I have to join all those bytes together. And I can do this with like this join syntax. Okay, and then I can print it. Or I can do like other things. Okay. And then this is like the flag, of course, could be different. The flag was stored in the challenge secret.y, which we did not see, just contains a variable. This could be like you submit this and you get points or something like that. So this is the idea. As we said, the code essentially implements what we discussed. Of course, there are like a bunch of indices. It's like one could implement this in different ways. But the main idea is this manipulation, this payload manipulation, this changing of padding, this guess, and to use the previous, the original bytes of the message. In TLS, now this is, of course, this is easy to exploit. In the actual real world, it can be a little bit hard because, for example, in TLS, there was this kind of vulnerability, but everyone was like, this is hard to exploit, things like that. Because if you have client and server, they communicate, they exchange messages protected, an attacker can take a message, change one byte of the padding, as we said, like it would be like this message called by index uguale. We are writing different bytes. The server, the vulnerable server, decrypted the message and then either said decryption failure for lack of padding or MAC incorrect. So this is like, this is the answer. But the thing is that, though, the issue was that this kind of message is not like you can, this error, this alert, it did not like to understand what has happened in the communication. It is not really clear because maybe the server tells the client with an alert which is also encrypted. So it is not really this easy to actually change. I think that what they did, I don't remember, like they implemented this, for example, to steal IMAP password, IMAP, because we have a mail server. The mail client, every like 2 minutes or something like that, sends the login, the credentials encrypted. And so I think that probably, I'm not sure how they measure the oracle. Maybe they saw if the connection was dropped. It signaled that something was wrong. So maybe they had this oracle and they waited for like every time the client connected, they changed one byte. So it took a little bit. So it is not really this straightforward. But yeah, so this is the general idea. Of course, in the wild, it is hard. But this concept of oracle is very, there are lots of different oracles, not only for CBC padding. Because IS is strong by itself, but it is just a primitive which has to be integrated in an ecosystem. If you do that integration badly, you get, you know, yes.